This presentation is going to be based on a couple of papers that were written together with some people, in particular David Gogolashvili, Luca Pellizzari, John Schoenmakers, and JJ Zhu. So what is the framework, or what is the motivation for this? It's to do with financial models with memory. So in recent years, I think it's fair to say that models with memory have become more and more important in math finance. So just a few examples. Of course, as Yuan said already, I am interested in rough volatility. And rough volatility, I put here one example of a rough volatility model, the rough Bergami model. And you see that, so this is a stochastic volatility model. So we have the typical dynamics of a stochastic volatility model with and this is where memory comes in, with an instantaneous variance process Vt, which is, in this case, a function of a fractional Brownian motion. And of course, if you write out the definition, or this definition of a fractional Brownian motion, which is not exactly the classical fractional Brownian motion, but what is sometimes known as the Riemann-Liouville fractional Brownian motion, you see that an increment of W hat involves the whole history of the driving Brownian motion W. So we have a process with memory, and in fact, this pair of processes is not a Markov process. But that's not the only class of models with memory. And by models with memory, I basically mean models which are not Markov processes. In finance, we have in order flow models, self-exciting jump processes, for instance, Hawkes processes. And beyond finance, there's also many examples, many applications of Hawkes processes in social sciences, in biology, in seismology, which is where this class of models originated from. And also outside Hawkes processes, we have, for instance, in statistical mechanics, the so-called generalized Langevin equations, or a very important concept in many engineering applications, so-called hysteresis, where, for instance, if you have a battery, like your mobile phone has a battery, and the the state of the battery, like, for instance, the capacity of the battery, the future evolution of the capacity of the battery, does not just depend on the current capacity, but it also depends on the way it was used before. So, for instance, how many cycles of charging and discharging, how fast charging and discharging happened, and so on. A classical example is magnets, actually. And models with memory, I think they are fun because they're challenging. And I'm always interested in computations and numerics. And from a numerical point of view, there's really many of our standard tools rely crucially on the Markov property. So that starts with, if we think about option pricing, that starts with PDEs. So pricing PDEs, for instance, they basically only work in a Markovian setting. But more generally, if you want to do approximation, functional approximation of any kind, so for instance, in the context of stochastic optimal control, if you want to compute conditional expectations, because we do this standard backward recursive formulation of a dynamic programming principle, we need to compute conditional expectations. And again, the Markov property is very helpful in order to actually allow us to efficiently solve these problems. Or to put it maybe a bit more, to put a kind of different point of view here, Of course, we can always think of any process, at least on an intuitive level, is a Markov process if I extend the state enough, right? So in the worst case, if you think about the dynamics of this fractional Brownian motion here above, if I extend the state to contain the whole history of the process, then I'm a Markov process, because then the present, the information about the past is contained in the present. Okay. But of course, from the point of view of functional approximation, this is really bad news, because this means that we have infinite dimensional state spaces, and therefore, I mean, the famous curse of dimensionality hits really hard. So in a way, non-Markovian processes with memory tend to have very high dimensional state spaces, even if they present themselves like this rough volatility model here, for instance, as a two-dimensional process. In some sense, there is an infinite dimensional process behind. So as a certain aside, and I want to go a little bit deeper into this question of, into the example of rough volatility models, also maybe in the context of, does the memory really matter? Because you might think it does not. And the reason is that, in a way, if you look at rough volatility models, we have, as we saw, we have this classical stochastic volatility dynamics on the stock price process. And then we have an additional process, the variance process, which does not necessarily, I mean, in this case, actually, we can think of a much more general class of processes than even rough volatility process, because at the end of the day, all we really need for the price process to be well defined is that the volatility process is, or the volatility process is adapted and square integrable. So you could think of something much more general than rough volatility. But still, the dynamics of S looks kind of Markovian, and as a matter of fact, you can kind of isolate this, let's say, quasi-Markovian structure of driving the price process, and you will get something like a BSPD in this sense, right? So for instance, basically, if we look at, so basically what I want to say is we can look at the dynamics of the asset price process as something like a Markov process in a random environment given by the variance process. So, and then if you were to compute a price, so say of a European option, so this would be the UTX, and of course the UTX here, X is kind of I fixed a level of the asset price process at time t. But of course, this is still a random field, because the environment, the V process behind it is not integrated out here in this conditional expectation. And then you see it satisfies a BSPDE. So we get this kind of additional part of the solution, which is necessitated by in order to kind of enforce the adaptedness. But however, what is in blue, it would be the standard, kind of heat equation dynamics for that you would expect from the kind of partial Markovian property. And this is actually not new, but this is applying results that have been known in the SPDE literature or BSPDE literature for quite some time. And in fact, this is only one possible approach. Another approach is, for instance, using path-dependent PDEs and or even rough PDEs. So in a way, we can isolate the memory, the effect of memory in this kind of problems quite precisely. And this allows us to do something like this. So what I'm looking at here is actually 4 trajectories of the volatility process, of the variance process, which happen to have the same terminal value. So I'm looking at let's say at an option which has a exercise state which is let's say 1 year in advance, but I'm looking at it at time 1/2. And at time 1/2, it turns out all these 4 trajectories of the volatility or the variance process, they end at the same point. Here it's 0.0825. And I'm looking at the values, these conditional expectations that we had before, basically the values of a European option at time 1/2. And you see the value obvious, I mean, as you would expect, as a matter of fact, it does depend on the history of the volatility process. Now, you also see that the dependence may not be very strong. So in a way, you would say volatility is kind of a higher order effect. I mean, the most important, the leading order term, if you like, is actually the asset price itself. But still, there is definitely a non-negligible effect of memory in this setting. So, coming to the topic of this talk, regression, for me, the application that I have in mind is stochastic optimal control, or to make it more concrete, optimal stopping. So I want to compute a random variable. I want to compute the value function Vt, the value process Vt. And of course, we know that if we think about a time discrete version of this, we know that dynamic programming allows us to solve this problem very easily. We take at any point in time t, we have 2 choices. We can exercise. If we exercise, we get the value phi of xt. If we continue, well, if we continue and the next exercise opportunity is at time t plus delta, then what we would get is the conditional expectation of the value at time t plus delta, given the current information. And of course, we want to maximize the value, so we are going to take whatever decision gives us the higher cash flow at this point. I put here an approximate equal because, well, this is a true equality in the discrete time case, but if you think about a continuous time case, when this is just a discretization, when this is just an approximation, then of course it's not a true equality. And the idea is now very easy. In the Markovian case, we just make the ansatz that, or we know that the conditional expectation is actually a function of the state variable xt at time t. And in the general case, well, what do we know? We kind of know, well, in principle, we know the same thing, but now we have a function of the trajectory of the path of this process x from the initial point in time, which I fixed to be at 0, but you could also think that you actually start at -infinity if you like. But let's make life simpler. We start at 0 up to time t. And now the problem, as I indicated in the very beginning, is a problem of approximation theory. Approximating functions suffers from a curse of dimensionality in the sense that, generically speaking, the higher the dimension of the argument x, or x restricted to the interval, the more difficult it is. And in the finite dimensional case, so I want to suggest that signatures, that means collection of iterated integrals, presents itself as a very natural way to construct such approximations on path space. Because of course here the idea is the argument x restricted to the interval 0t is an element of a path space. And I mean, I'm very ambitious, but I already know I will fail in my ambition. I want to talk about the global regression as well as local regression, but actually I think we will stick with local regression, but never mind, we will come to this in more detail later. Right, so what is the signature? We start with a path, let's say from 0 capital T to RD. And because I don't want to talk too much about what integration means, I'm going to assume that the path is smooth. We will, I think, talk about it a bit later, what we really mean. And for reasons that I will also indicate a bit later, I will attach an additional coordinate, namely the running time, to the path. The reason why I want to do that is because, I mean, in many applications, let's start from the other way around. In many applications, we are interested actually in functions on path which are invariant under time parameterization. And it turns out the signature that I'm introducing here actually does that. However, for optimal stopping or optimal control, that's not quite true. Time has a meaning, and we cannot just ignore time. So we want to attach time to the path so that we lose this invariance under time reparameterization. Okay, so what is now the signature? The signature, very simply, is the collection of all iterated integrals of this path, of coordinates of this path against each other. And it's indexed simply by, well, you could call it multi-indices, but for reasons, for some reasons, I prefer to think about this as words, actually. So this is a word in the alphabet from 0 to D. And there are some operations that make a lot of sense in the context of this structure of the signature, or also words. So we can add iterated integrals, we can multiply them with scalars, but in particular, we can look at concatenation of such words. So there is a product structure, the concatenation product. And that means we can put a algebraic structure, we can put signatures in an algebraic structure, and I know most talks on signatures do this. I'm not going to, I mean, I'm minimizing this for the purposes of this talk, but I want to say that there are good reasons to actually study this and use this algebraic structure, in particular if you want to take advantage of certain redundancies of features of the signature for computational or analytical purposes. But in a way, what is really going on here is we are looking at this kind of series of all iterated integrals, and we consider it in a way as a formal power series, but a formal power series in non-commuting variables, right? So what I'm thinking of is, instead of ignore that there's an integral, and let's pretend for a moment that what is here is actually a monomial, right? So I ignore this integral sign and ignore these d terms and just look at this monomial. And then, of course, in a way, the associated formal series will be a series with commuting variables because, well, these terms, these monomials are commuting. But if we now take iterated integrals instead, they are not commuting. So if I change the order of my indices, there is no reason why the iterated integral should stay the same. And generically, it will not. Therefore, we can really think of this as an object which is a formal power series, but a formal power series in non-commuting variables. This is kind of the big difference to the polynomial case somehow, to the finite dimensional case. Right. And why do we like, or why is the signature a good object for the purposes of this kind of approximation question, of computing conditional expectations, for instance, or more generally for approximating functions on path space? The first property to keep in mind is that it turns out the signature determines the path. Now, there are some caveats here. The first one is, well, obviously, the signature only sees the increments of the path. So the signature does not know the starting value. Okay. Up to this, however, it is actually true. And this statement is true because we use this time extension x hat. Remember, x hat was defined as our path x with an additional coordinate, which is running time. Otherwise, as I said, otherwise what would happen here is that the signature determines the path up to the starting value and up to time reparameterization, or more precisely, up to so-called tree-like excursions. Right. And as a consequence of this, and some structural properties of the signature, it turns out that we can use the Stone-Weierstrass theorem because the linear functionals, and here I really mean finite linear combinations of iterated integrals, linear functionals of the signature form a subalgebra of the continuous functions on path space, which is point separating. This is because the signature determines the path. It's nowhere vanishing. Well, and it's a subalgebra. And therefore, the Stone-Weierstrass theorem says that it's dense in the continuous functions on path space. So the set of linear functions of the signature is dense in the set of continuous functions on path space on compacts. This is, I think, an important restriction to make here. The Stone-Weierstrass theorem only applies to compact sets. And of course, in the context of path space, this is a big restriction because path space, I have not been very precise in what I mean, and I may not actually become very precise in what I mean by path space. Think of rough path spaces. These are infinite dimensional spaces. And generally speaking, compact subsets of infinite dimensional spaces are very small. So, this is a restriction that we are going to have to work a bit to overcome. Right. And now let's look at the first application. And I'm going to look at local regression on path space. And here, let me actually abstract a little bit. Instead of talking about path space, I'm going to think of a generic metric space. So in particular, this is nice because if you know rough paths, then you probably remember that the space of rough paths is actually a metric space. It's not a Banach space or something like this. So it lacks the linear structure. It's just a metric space. So we have a metric space, and we have a function from that metric space to the real numbers, and we want to compute the condition. So we have a random variable taking values here in the metric space. We want to compute the conditional expectation. And we are going to consider a semi-metric row on X. We actually only need a semi-metric, and this will become very convenient later on. And if we want to do this kind of analysis, there are kind of two important and somewhat counteracting properties that one has to keep in mind. The first one is we want the function that we want to approximate. So the smoother, the more regular the function, the more easy it is to compute such an approximation. And we are going to measure this kind of regularity in terms of Hölder regularity. So basically, our function f, and here I write capital F to indicate that we are now in a larger class here. We say that it's beta Hölder if the standard definition of beta Hölder is satisfied with respect to this semi-metric on our metric, well, on our path space in essence. Now, the second ingredient is small ball probabilities. So basically, we need to, in the end, we are going to use sampling methods. So we are going to use regression. That is, we have samples of the random variable x. And again, x is going to be a process, a stochastic process, right? So we are going to base all of this on samples, and in a way, we need to understand how far away are these samples from each other. And this is encoded by small ball probabilities. So nothing but the probability of a ball of radius h in this metric space. And what we're going to use is the classical Nadaraya-Watson estimator. And actually, one of my co-authors here in this paper, David Gogolashvili, he told me that he wrote his master thesis, was supervised by Nadaraya in Georgia. So there is well, I guess a personal connection to this estimator here, all very classical stuff, I guess. So given a kernel K, and this is, and just to be clear, this is now a kernel in the sense of real numbers. So this is a function from R to R, and the bandwidth H, the local regression estimator, the Nadaraya-Watson estimator, is defined by, okay, I have my function, I have my point X. I look at all samples which are close enough to X. These are the XMs where the rho is kind of small enough. And I take a weighted average of the corresponding values of Y. Okay? I mean, I have never, and I don't assume that K has a bounded support or a compact support, but still, I mean, in a way, this is the idea. And it turns out that, and this is, I think, a somewhat classical, but I mean, I think this precise formulation, I think, is new, but for expert, this would not come as a surprise. We see this kind of error estimate of our estimator compared to the true function f. So we have two terms. We have a bias term, which depends strongly on the smoothness beta. And we have a variance term, which depends on the number of samples as well as the small ball probability. So again, here the idea is this is an estimate with high probability. So with probability at least 1 minus delta, this inequality is satisfied. And now, again, this was a very, very general framework, so semi-metric space, basically. And the question is now, what do we get out of this? And the situation that we typically have in mind is, of course, the finite dimensional case. And in the finite dimensional case, this small ball probability, well, what happens here? I mean, think about it like this. Assume that capital X has a density with respect to Lebesgue measure. Then, in a way, the probability, such a small ball probability, is going to be proportional to the volume of this ball according to the Lebesgue measure times the density. The density, let's say, in the center of the ball. And this means that the small ball probability typically behave like h to the d. D is the dimension. And then the next step is we are going to equate these two error terms because we don't want to, I mean, in order to be optimal. And what this means is a very classical result for the asymptotic error as a function of the number of samples m. And you see the curse of dimensionality in D. As D increases, this power becomes worse and worse. Okay, so this is the finite dimensional case. What happens in the infinite dimensional case? And in the infinite dimensional case, typically what happens is you expect this kind of exponential behavior of these small ball probabilities. And therefore, what this implies would be something like a logarithmic error in terms of the number of samples. And in a way, just as an example, there is a paper of Li and Zhao from 2001 who actually compute this for the fractional Brownian motion. So here, path space, I think, is taken to be the alpha Hölder. Yes, it's the alpha Hölder functions. Rho is the alpha Hölder norm. Alpha smaller than h. Then in this setting, you can compute the small ball probability for the distribution of fractional Brownian motion. And you exactly get this kind of exponential decay with a power gamma that then, of course, depends on h, on the Hurst index. So I say this on the one hand, it's kind of nice to have guarantees of rates of convergence. But on the other hand, since we are working in infinite dimensions, we have to kind of curb our expectations because we cannot really expect generically to see something much better than this logarithmic behavior of the error, unfortunately. So a signature doesn't, you can apply this to different metrics which are inspired by signatures or rough paths, and the theory goes through. And as expected, we kind of get these logarithmic rates. So for instance, if we take the alpha Hölder rough path norm, I have not introduced what rough path is. If you are an expert in rough path, then you will understand. Otherwise, you could think of, I'm kind of repeating the example of the fractional Brownian motion, but the important difference, and again, I'm talking to the experts now, this is really the rough path metric now, not the standard alpha Hölder norm. This is the alpha Hölder rough norm. And then William Salkert, a couple of years ago, he actually computed the small ball probabilities for Brownian motion, so more precisely for the lifted Brownian motion in the rough path sense, and you get exactly this logarithmic behavior. However, and here it becomes important that we did not require rho to be a metric. You can also do something much more naive. You can just say, for instance, let's take a truncated signature, and let's compute the Euclidean distance between my truncated signatures. My metric, so x, y are two paths. I compute the truncated signature up to some level k of path x. I compute the truncated signature up to level k of the path y, and then I take the Euclidean distance between those two guys. That's what I do. And in this case, again, the theorem applies because it only requires a semi-metric. You're actually effectively in the finite dimensional case, because what it boils down to at a certain level is you have to think of the free Lie algebra of degree k, of the free nilpotent Lie algebra nilpotent of degree k on RD, and the dimension in which you're working here is really the dimension of this free Lie algebra. You could also talk about, of course, the dimension of this space where the iterated integrals up to degree k live, but that is higher. So basically, if you want to get more sharper estimates, you want to restrict yourself. It's like, so basically the truncated signature lives in a subgroup of that space, and this here gives you precisely the dimension of this subgroup as a submanifold. And then the small ball probability are exactly of the form h to the power of h to this dimension. And therefore, you would then get an estimate of the, finite dimensional version, a finite dimensional estimate. The only problem is, well, do we know good examples of Hölder continuous functions under this semi-metric? And my answer is no. I mean, of course, you can take linear functionals of the truncated signature. Okay, that's going to work. But that seems like a very, very restrictive example. But for instance, if I take the rough path Hölder norm, then a very nice and interesting example of a, in fact, Lipschitz continuous function is the solution map of an STE. So basically, in the first case where our metric, actually it's a metric, is the rough path metric, then there is actually a very rich class and very interesting, very rich class of Hölder continuous functions, in fact, even Lipschitz continuous functions, including the solution maps of rough and then also stochastic differential equations, assuming that the driving vector fields are nice enough. Right, and then I'm going to show you a couple of plots, but basically we were very happy with this result because this is, if you put this together, what this gives you is a precise or a provable rate of convergence for the task of learning the solution map of a stochastic differential equation using this kind of rough path metric. Or if you want to use signature, well, we don't know that the solution map would be Hölder continuous, and in fact, you would not expect this to be the case. But on the other hand, as we will see in practice, it seems to work really well. So, okay. And so this was, we're very happy with that part, that this is, I think, I would say maybe the first really rigorous proof of or rigorous rates for machine learning applications using signatures. And they have been used quite a lot on a more empirical level. On the other hand, of course, if you compare it to state-of-the-art machine learning methods, this local regression using signatures will not, will not be able to outperform them. So they will not be able to compete. Yeah, so of course, on the flip side, again, it's much faster because unlike, let's say, we do a state space model based on deep neural networks, then training is very, very computationally intense, whereas in our case, we just do this. It's immediate. Right. And you can see some examples here. So basically what this plot says is that, the problem is a little bit, here it's important that I use the rough path Hölder norm, not the standard Hölder norm. And that one is expensive to compute, very hard to compute. So basically what this plot says is that if you have this fast converging curves at the bottom, these correspond to the truncated signature metric. And the example here is actually learning the solution map of an STE. So those seem to converge very fast, but of course, they do flatten out at some point. I mean, at some point, the degree, okay, in this case, degree 2 signature is just not enough, doesn't contain enough information. And at that point, you flatten out. And at some point, we don't see it in this plot, but at some point, the same would happen for degree 3 or 4 truncated signature. On the other hand, if we compare to classical competitors, for instance, here the black triangles, this is the L1 distance, the gray, what is this? The gray multiplication sign, this is the L2 distance, or even the one variation distance in which you don't have convergence at all. So basically for these, they are clearly outperformed by this signature methods. Yeah, and here is a runtime comparison where again, these, where we basically see if we take p-variation distance, runtime actually, they are very unfavorable regarding runtime. So the bottom line is from the examples, so this is just one example. We also applied it to one of the standard collection of data sets for classification tasks for time series. Basically, it's a similar outcome. So basically, the bottom line is a little bit for the alpha Hölder norm, we have provable bounds, but the performance is not so great. For two reasons. Number one, because computation is very expensive, but number two, also the signature does contain, in I think very efficient way, a lot of crucial, important information about the path. If I take truncated signature, there cannot be a convergence, for instance, for the example of learning a solution map of an SDE, but the performance in practice seems to be really good, and this is also in a way supporting the many application papers using signatures where in the end it boils down to using this kind of truncated signature approximation. So if I had more time, I would be prepared to tell you about global approximation as well, and I'm going to largely skip that, I think. Yeah, maybe let's, okay, no, but.
5 minutes.
Yes, so basically in the end, it boils down what this theorem says, and I appreciate that it's probably not really possible to read at this point. You can approximate pretty much arbitrary, let's say, p-integrable stochastic processes on the filtration generated by a rough process X. You can approximate them all in LP with respect to actually linear functionals of the signature. And with that, let me actually come to some further examples for the last 4 minutes or so. I'm going to look at Bermudan option pricing and rough volatility model. We are looking at 2 examples, rough Bergomir and rough Heston. And the idea is we are going to use 2 classical algorithms, Longstaff-Schwarz, and a dual approach, which are classical in the context of Markovian models. And we are going to kind of apply them using signatures or some version of signatures as a feature set. So basically, we extend the non-Markovian process to a kind of Markovian version using signature, except that, of course, we have to truncate the signature so that in the end, we are still committing a crime here. And I mean, there are lots of different, so these are the 2 basic algorithms, and we apply different versions of signatures in a way. We either apply linear functions of the signature, we apply neural networks applied to truncated signature, or we also apply signature kernel, which is actually special because it does not involve a truncation of the signature. And the precise choices here were for each combination of signature approach and algorithm, we tried to kind of find the optimal variables to proceed for the, so that we try to be really fair here. And at the end of the day, there's always a lower biased and a higher biased value. And basically, if we take as an example the Raff-Bergome model computing put options, we see that well, let's put it like this. I think if I wanted to draw some conclusion here, for the Longstaff-Schwarz algorithm, linear functionals of the signature actually perform very, very well. For the dual method, they don't perform well at all. And in the end of the day, the deep neural networks applied to the signature seems to be the best compromise compared between accuracy and computational time, because unfortunately the signature kernel, even though it actually performs pretty well, accuracy-wise, it does not. It has by far the highest computational cost, and from that point of view, has a problem. And you see that compared to earlier attempts in the literature, for instance, a paper by Gudenesh, Manzotti, and Zanetta, I think, we see quite some improvement of the duality gap, but at some, especially in the Raff-Heston case, you see that in some parameter regimes we have still left with let's say 4% duality gap, so it's still not there, still room for improvement. Maybe interesting last slide. We also tried to look at, once again, coming back to what I showed you in the very beginning, is the non-Markovianity really important? And here the thing is, some of the iterated integrals are actually nothing but polynomials. So basically, whenever you have, for instance, here, whenever you have a word which is, let's say, 2, 2, 2, this is just an increment to the power 3. So this is actually, if you want, a Markovian feature. On the other hand, if you have mixed terms, 2, 1, 2, this is a truly non-Markovian feature, because this is not just the function of an increment. There's real integration happening. And you see, okay, the most important features tend to be Markovian features, let's say xt itself, then this is, I think, the variance, the increment of the variance. This would be the increment of the variance squared. But you also see there is some significant non-Markovian features as well. And with that, let me thank you for your attention.
Okay, so thank you very much, Christian, for your very nice talk, very interesting talk. So now we go to the questions. So if you have any question in the audience, please write in the chat, and I will transfer to Christian. So Christian, can you see the? So we have first question by Kamiayati, and the question is, what is dependent and independent variable in regressions?
Okay.
Can you see the? Can you see the?
In the example? Okay, here. Yes, okay, here I see. Yes, now I see the question. The problem is, now that I see the question, I don't see my slides anymore because it takes up quite some space. I'm trying to, I'm trying to, yeah, right. So you mean in the context of the examples? Well, in the context of the examples, let me go to the beginning. I'm talking about this kind of situation. So I have a process. In this case, generically, it would be, think of the Raff volatility model. So this xt is the pair st and vt. St being the asset price process, and Vt being the variance process. And I want to compute the conditional expectation of, well, the value of the American option in the future, t plus delta, conditioned on the path of this process x up to time t. So this is the situation that we should think of. But more generally, y is a function on path space, and x is a process. X is a realization of the process of a process. So think of y being the solution at time t, at the terminal time, for instance, of a stochastic differential equation driven by the process x. And I do appreciate that there are a couple of x's here and there which are probably not always consistent. Sorry for that.
Okay, thank you. So we have other question by Ali Reza Mousavi, who are actually three questions, but maybe let's start with the first one. So how do you find the optimal truncation level, and is it related to the roughness of the path or not?
This is actually a very good question. And my answer is, I wish I knew. I mean, to be maybe a bit more precise, you are actually, so the roughness of the path is one aspect. So you're thinking of the Lyon's extension theorem, which basically says that, or more precisely, the standard theory of rough path, which basically say that if, for instance, you want to solve a stochastic differential equation pathwise, you need to have as an input not just the driving path, but also some of its iterated integrals. And there it's true that the level of the iterated integrals you need depends on the roughness of the path. But here my problem is a little bit different, because here I have a, let's say, generic nonlinear function of path space, and I want to approximate it by, let's say, linear functions of the signature. This is a problem even if the path is smooth, and from a theoretical rough path point of view, I don't need any iterated integrals. So I would say this is more related to the regularity of the function rather than the regularity of the path. But of course, think about it in the finite dimensional analog. You have a generic function from Rd to R, and you want to approximate it locally by polynomials. It's not trivial at all to choose the degree of the polynomial, I would say, generally speaking. I mean, okay, in the finite dimensional case, there is, of course, a lot of theory on what to do. But here, I think that's the analog to think about, actually. And in fact, in finite dimension, the opposite is true, right? I mean, if the function you want to approximate is not very regular, you would not want to use very high degree polynomials. And you would only want to use high degree polynomials if your function is regular.
Okay. Maybe a last question. So does it method work for discontinuous approximation, say pure jump or not?
So if, okay, there are two ways to read this question. Number one, the function we want to learn is discontinuous. Number two, the path is discontinuous. If the path is discontinuous, you can define signature as well. And then this method in principle works as well. If the function is discontinuous, I would be more careful. So I think also in finite dimensional cases, if the function is discontinuous, what we try to do typically is, I think, to identify where the, let's say, jumps of the function are, and then kind of dividing the domain into two parts, basically, so that we solve different approximation problems somehow on two parts of the domain. So, and I think this is also what you would like to do in that case on path space.
Okay. Okay. So I think there are no more questions. So we can thank again Christian for your very nice talk and
Thank you
stop
very
the
much.
session. Yeah, thank you. So we shall now close the session. So the next SIAM BFS seminar will take place in 1 month exactly, in March 12th with Eduardo Abijaber. I think we will give me probably a related talk also about signature memory formats. So it will be fine. And okay, so on this, hello everyone and see you in 1 month. Bye bye, Christian.
Bye bye.